In this circuit, we have two loops of wire, and we are interested in finding the transfer function that will take us from the input voltage on the left-hand side to our output voltage across capacitor C2. So with these two loops of wire, we're going to have a little bit more complication in using our KVL equations to generate equations to get to our transfer function. So ultimately, we want to find, well, the transfer function given above. I'll call it G is EO over EI. So let's make our diagram, which will look a lot like the given one, but we'll be able to mark it up a little bit more. So in the bottom left, I will call this node A. We're going to go across EI. We'll see that that is the voltage between A and the top here. Then go through resistor R1, have another node, then we come down, capacitor C1, and then we can come back to A. I will use the given current, assuming that I1 is going to be positive in the clockwise direction, and I'll just stick with that. Then put on the second piece of the loop, we go through R2 and get to a node, then come down and we have a C2 capacitor, and then come down and then come back. And again, I will stick with the assumption that I2 is clockwise in this loop. Now, each of these current loops are only in that kind of square or rectangular area that they circle back on each other with this method. And then coming out here, ultimately what we're interested in is this EO. We want the voltage across that capacitor C2. And I will call this point B, which we'll use in a second when we start to develop our equations. So in the equations, I'm going to use KVL for my first equation, as we see. So from KVL, this will be equation 1. If I sum the voltages, or the voltage drops really, as I go in this one, I will go A back to itself. Now, there's not a unique way that we can do the voltage loop. I'll show one way where I'm going to start at A and come back to A, but there's different things we can do as well with even starting at A and coming back to A, but we need to have unique equations for the outputs that we discover as we develop these equations. So if I start at A, I am going to go in this first one, starting at A, and go across EI to the point up here. So along that path, I have passed through little e sub I, but we are working in the frequency domain, so I'm adding to this e sub I. I'm assuming that that is going to be the positive direction of e sub I, and I'm going with the direction of current I1. So I'm at the upper left, I'm going to cross over R1, and I'm going to get to this point. Now notice the direction that I1 is going. As I go from that left node across R1 to that right node, I'm going with the direction of current, at least that I'm assuming is the current's direction. And there's a voltage drop then as I go with the direction of current. So there'll be a negative, and then the voltage drop across a resistor is going to be its resistance times the current going through the resistor. So R1, I1. Next, I'm going to choose to go from my current position up here down to point B across capacitor C1. So I'm going here with the direction of I1, but when I subtract here, I'm going to have a 1 over CS, C1S happening. The tricky part about C1 is that it is affected by two currents, I1 and I2. So here on the left-hand side, when I get across C1, I1 is going down, but on this side, I2 is going against it. So actually what's happening here is that there's the sum, or the net current going through it, is actually the current that I'm going to multiply by the 1 over C1S. So positive I1, because that's going with us, and that negative is already taken care of out front, and then minus an I2, because I2 is going the other way. So again, as we travel from that midpoint down to B, we're going with I1, but against I2. So that's where I'm getting this negative 1 over C1S times that quantity I1 minus I2. So I'm at point B, and I'm going to choose to return back to A. And now I have completed my loop. I started at A and I ended at A, and I got one of my KVL equations. All right, so that sums to 0 by KVL. I'll get rid of these, and then I'll start a second equation. So I'm going to do KVL again. Well, actually, before I do that, let's start looking at what do we have as our inputs and our outputs. So in this equation, my input is actually EI, that's my dependent variable, but I'm told that that is the input into the system, that's what we have control over. And what outputs did we find along the way? Well, we have I1, that current in the first loop, and I2. So actually 2 outputs appeared in that first KVL equation, and only one input, EI. But if we go back where we're trying to find, we want E out over EI. Well, E out doesn't even appear in that first equation, so definitely we're going to need more. Also, we have 2 outputs so far and only 1 equation, so that also tells us we need more equations. So what I can do here is I'll choose to do another KVL equation. I will do it voltage starting at B. Now I could start at A again, and instead of going down across C1, I could have gone across R2 and then down C2 and then come back. And that would actually be another KVL equation I could use, and that would be fine. I'm going to choose to do it a little bit different. I'm going to start at B, and I am now going to travel up to that top middle node. So as I do that, I'm going to have immediately a voltage drop because I'm going across a capacitor here, so minus 1 over C1s. Now here, because I'm going from B upward, I'm actually, from this direction, going with I2, but against I1. So notice that inside here it's I2 minus I1, and in my first equation where I was coming from the top to the bottom, there I was going with I1 against I2, so I had I1 minus I2. So different direction, so the opposite signs inside this equation. Now here, I'm at the top node. I'm going to go across R2 to that right node. So here, I'm going with the direction of I2. I2 is the only current that is going across R2, so it's just going to be a minus R2 I2. Now I am at the top right. I'm going to travel down here. I'm going to go across capacitor C2. So again, I'll have a voltage drop as that happens. I'll have a 1 over C2 times S. And here, there's only one current going across C2. That E out is just measuring the voltage across the capacitor. That's not another loop in the system. So the only current here is I2. So for my second KVL equation, I1 and I2 are still here. And actually, I haven't added any outputs into this system, nor inputs. There's only a single input into the system. So I actually have enough equations at the moment. However, I don't have any equations still that has E out. So I definitely still need a third equation in order to do this. All right, so the last thing I need is something with E out in it. So what I can do is I'll go from here, that top right to the bottom right across C2, because what I can say is that minus 1 over C2s times I2 is equal to going across E out. All right, so there's kind of this implied direction of these source voltages or output voltages here. So I can say that negative 1 over C2s I2 equals negative E out. And for simplification, since they're both negative, those negative signs are going to cancel out. So I get 1 over C2s I2 equals E out. So why did I do that? I've added now a third output, but it's an output I needed in order to get what I need in the end is that specific transfer function of E out over EI. So the way I did this, I used 2 KVL equations to get 2 of my equations. So I started at that lower left node and made that small rectangular path and came back to it. I then started at node B and made a small rectangular path and came back. And then I looked at the equivalent voltage, or just the voltage across that capacitor, which was 1 over C2s I2, and that's ultimately the voltage that I care about, that E out. So I do have a solvable system I'm going to put into Mathematica in order to get my desired transfer function. Along the way, I can also get I1 over EI and I2 over EI. I don't need it for this, but it's part of the process of using Mathematica to do the algebra for us. And again, I want to note that the equations I developed, at least the KVLs, are not unique. There were other paths I could have certainly taken. My equations would have looked different, but ultimately I can only get so many linearly independent equations that these two are all I need in order to derive my transfer function. All right, now we're ready to put this into Mathematica and let it do the heavy lifting for us with the algebra. So first I need to input my three equations here. So I have KVL1, I will call it, and that is on the left hand side 0 equals, I have EI minus R1 I1 minus, and I will use the fraction here of 1 over C1s, and I have for the first equation I1 minus I2. All right, so that's KVL1. Now I will enter KVL2. So KVL2 is also 0 on the left hand side, and that was I'll copy this. But this is, remember, I2 minus I1, since I went in the opposite direction, minus R2 I2 minus, and here I have the 1 over C2s times an I2. And double checking this looks correct for what I have. And then the third equation, that is just saying what is the voltage drop across the capacitor, since that's ultimately the output voltage that we are trying to monitor. So I'll just call it EQ3. It's not coming from a KVL, and I can just copy this to save a little bit of effort, equals EO. All right, so those are our three equations here. Remember, we have three outputs, I1, I2, E out, or EO, and that one input EI. And we have to keep that in mind when we are doing our solve. What are we trying to solve for? The outputs. So solve the equations KVL1, KVL2, and what I call EQ3 for I1, I2, and E out. Right, it solved them. I'll clean it up just a little bit here. Okay, so these are what will become three transfer functions, although we only care about one here. We only care about E out over EI, which is what we're going to proceed with. So we have I1 and I2, but we won't need it. So our transfer function G is what I called it above. I can take the E out expression, and remember G, the transfer function, is E out divided by EI, so I divide both sides by EI, and that becomes 1 in the numerator. And I will again let Mathematica do the grouping for us, so I want to collect the numerator of G on my S terms, and the same thing with the denominator. All right, so now it's properly grouped our S terms together. We have those different parameters in there. So this is the transfer function that we're going to be interested in. We're just going to have to rewrite it to be in the standard form that we want for these types of problems. Okay, so Mathematica gave us the output, but we want to put this in descending order, the powers of S. So this is E out over EI, the transfer function we wanted. So the numerator is fine, 1. And now I just have to reverse the order here, C1, C2, R1, R2, S squared. And then the middle term, I have C1, R1, C2, R1, and C2, R2 times our S term, and then plus 1 at the end. And that's it. That's the one transfer function that we were looking for here, the voltage across the capacitor as our output versus that source voltage EI being our input. And just briefly going back, how did we get to this transfer function? Here we had this slightly more complicated circuit where we could make two loops and have this I1 current in the first loop and I2 current in the second loop. And what we did was redraw that diagram, and what we're interested in finding is the E out over EI for our transfer function. So I used two KVL equations. I chose to start at A, do this small loop and come back on itself, and then for a second equation go from B and do this small loop and come back on itself. Again, this was not a unique choice that I could have made. There's other loops I could have chosen, but I needed two different loops in order to get these two equations. Counting up my outputs at this time, E out did not appear yet. However, that is ultimately the output I need for my transfer function, so I needed a third equation to look at the voltage drop across the capacitor, which is E out. Used Mathematica to take these three equations to get three transfer functions, or effectively three transfer functions for I1, I2, and E out over EI, but only needed the E out one. So I got that expression and then rewrote it so that I have it in my standard form here. I have just a 1 on top, and I have descending powers of S in the denominator with the parameters and the coefficients spelled out here with the two given capacitances C1, C2, and the two resistances R1 and R2.